On a particular night in late 2024, an automated telescope in South Africa registers a faint point of light moving against the fixed stars. The detection is routine, logged by software before any human eye sees it. The coordinates place it in the southern sky, somewhere between constellations whose names were chosen by navigators centuries dead. The light is dim magnitude 19 or 20, visible only to instruments designed to capture photons that have travelled vast distances to reach polished mirrors and silicon sensors. The observatory's algorithm flags the object for follow-up observation. Movement suggests it is not a star. Brightness suggests it is not a planet. The trajectory, when calculated over subsequent nights, suggests something rarer still. This is 3I Atlas. The designation is bureaucratic, assigned by the International Astronomical Union's naming conventions I for Interstellar, 3 because 2 others were confirmed before it. Atlas refers to the telescope system that found it Asteroid Terrestrial Impact Last Alert System, a network built to watch for rocks that might one day threaten Earth. Instead, it finds a visitor from another star system entirely. The discovery announcement circulates through astronomical networks within days. Observatories across continents begin tracking the object, gathering light, measuring velocity and spectrum, attempting to understand what has arrived. The comet is not dramatic. It does not blaze across the sky. For most humans, it remains invisible, a mathematical abstraction moving through databases and research papers. Only the largest telescopes can resolve it at all, and even then, it appears as a smudge, a diffuse glow with no sharp edges. But the mathematics reveal what the eye cannot 3I Atlas is moving faster than gravity alone would allow if it had originated within our solar system. Its velocity vector points backward to a region of space between stars, to the cold galactic medium where matter drifts in isolation, unbound by any sun's embrace. This is how astronomers know it is interstellar not by appearance, but by the shape of its orbit, the hyperbolic curve that passes through and does not return. Somewhere in the history of this comet lies a star system it once called home. Perhaps it formed in a protoplanetary disk 4 billion years ago, or 5, or 6. Perhaps it orbited a sun not unlike our own, or a red dwarf cooler and dimmer, or a binary pair locked in mutual revolution. Perhaps it was ejected by the gravitational tug of a giant planet, flung outward at speed sufficient to escape that star's gravity entirely. Or perhaps its parent system was disrupted, another star passing close, or the shock wave from a nearby supernova, scattering debris across light years. No record of that departure exists. No instrument witnessed the moment 3I Atlas left its origin behind. What follows is a voyage measured not in years but in epochs. The comet drifts through the interstellar medium, mostly hydrogen, 1 atom per cubic centimetre on average, with trace amounts of helium, dust grains smaller than bacteria, ionized particles pushed by stellar winds from distant suns. It is not empty. There's space between stars, but it is profoundly sparse. Collisions are rare. Radiation from the galaxy's spiral arms bathes the comet in low-intensity cosmic rays, slowly altering surface chemistry, breaking molecular bonds, darkening ice into complex organic tars. Time passes in quantities difficult for human cognition to grasp. 1 million years, 10 million, perhaps 100 million, depending on how far 3I Atlas has travelled and how fast it has moved through the dark. The comet does not know it is moving. It has no awareness, no memory of the star it left or the star it approaches. It obeys gravity and momentum, tracing a path determined by forces applied long ago and never quite dissipated. The universe is patient with such objects. There is no hurry. There is no schedule. A comet may wander for 1 billion years and encounter nothing, or it may pass through a molecular cloud, or graze the outer halo of a globular cluster, or fall into a new star system entirely by accident of trajectory and timing. And then gravity begins to curve its path. Our Sun, a middle-aged G-type star, exerts influence across distances that seem almost negligent. At 1 light-year away, its gravity is faint, barely sufficient to tug on passing objects. But over time, over the slow accumulation of centuries and millennia, that faint pull compounds. 3I Atlas, approaching from the galactic north, begins to bend toward the plane of the solar system. The change is gradual. If one could watch from outside, time-lapsed across 10,000 years, the comet's path would appear to arc gently, a curve drawn by invisible hands. The sun does not capture it. 3I Atlas is moving too quickly for that, but it does alter the trajectory, pulling the comet into a long swoop that will bring it closer to the inner planets than it has been to any star in uncountable ages. No fanfare marks this approach. The solar system does not notice. Earth continues its orbit. Humans continue their lives, unaware that something ancient and foreign is falling sunward, carrying ice from another star's fusion, molecules assembled in a nebula whose light has not yet reached our eyes. Only took a few million years to get here, and now, for a brief moment in cosmic terms, 3I Atlas will be visible, measurable, knowable before it leaves again, this time forever. To be interstellar is to carry chemistry that does not belong here. The molecules frozen into 3I Atlas were not forged in our sun's protoplanetary disk, not shaped by the same proportions of elements, the same temperatures, the same radiation environment that built the planets and moons and asteroids orbiting this particular star. When astronomers analyze the light passing through the comet's atmosphere, when they break that light into component wavelengths and match absorption lines to known molecular signatures, they are reading a chemical fingerprint from another stellar neighborhood entirely. The ratios matter, the isotopes matter. Carbon-12 versus carbon-13, nitrogen-14 versus nitrogen-15, oxygen-16 versus its heavier siblings. These ratios vary slightly from star to star, depending on the star's mass, age, metallicity, and the history of nucleosynthesis in the galaxy around it. Water ice dominates the comet's composition, as it does for most comets, but the water itself may differ in subtle ways. Deuterium hydrogen with an extra neutron appears in varying concentrations depending on where and when ice forms. In our solar system's comets, the deuterium to hydrogen ratio clusters around certain values, reflecting conditions in the sun's natal cloud. If 3I Atlas shows a different ratio, it suggests formation under different thermal conditions, perhaps around a cooler star, or in a molecular cloud with different chemical enrichment history. The difference might be small parts per thousand, but measurable. Spectroscopy is precise enough now to detect these variations, though the comet must be bright enough, close enough, and observed with sufficient resolution for the analysis to succeed. Carbon monoxide outgasses from the nucleus as sunlight warms the surface layers. This molecule freezes at very low temperatures, around 25 Kelvin, and sublimates readily as the comet nears the sun. Its presence indicates that 3I Atlas retained volatiles through its long journey, that it did not lose all its frozen gases to cosmic ray sputtering or collisions with interstellar particles. The universe is not kind to surfaces exposed for millions of years. Radiation darkens ice, polymerizes simple molecules into complex tars, slowly erodes the outer layers atom by atom. Yet beneath that processed rind, the original chemistry persists locked in cold storage, waiting for warmth to release it. Cyanogen appears in the spectra as well, a compound of carbon and nitrogen, mildly toxic to human biology but common in cometary environments. Its presence tells astronomers something about nitrogen chemistry in the comet's birthplace. Ammonia might also be present, though harder to detect. Methane, methanol, formaldehyde. Each molecule a small piece of the puzzle, each one revealing something about temperature and pressure, an elemental abundance in a place we will never visit. The comet is a library written in ice, and light is the tool we use to read it. There is no way to know, with certainty, which star system 3I Atlas originated from. Tracing its trajectory backward through the galaxy is possible. In principle, astronomers can calculate its path through space. accounting for the sun's motion, the motion of nearby stars, the gravitational perturbations from massive objects in the galactic disk. But the uncertainties multiply over time. A small error in velocity measurement, compounded over 1 million years, translates to vast differences in possible origin points. The comet might have come from a star a few dozen light-years away, or several hundred, or more. It might have been wandering for 10 million years, or 100 million. The galaxy rotates, stars drift in their orbits around the galactic centre, and the exact configuration of the local stellar neighbourhood changes over such timescales. Backtracking becomes speculation after a certain point. What remains is inference. If the comet's chemistry resembles that of certain classes of stars, if the isotope ratios match models for red dwarf systems, or metal-poor stars, or young massive stars with high ultraviolet output, then astronomers can narrow the possibilities, but they cannot point to a specific star and say, "There, that one, that is home." The universe does not leave such clear trails. Even if 3I Atlas passed within a light-year of its parent star 1 million years ago, that star has moved since then, following its own orbit through the galaxy, and the comet has moved as well, and the angles no longer align in ways that permit certainty. Still, the attempt is made. Researchers model trajectories, compare chemical signatures, search databases of nearby stars for candidates that might have harboured this object once. Some stars can be ruled out too young, too far, too chemically dissimilar. Others remain possibilities, faint and uncertain, entries in a catalogue of maybes. The comet does not care. It carries no memory of origin, no longing for return. It is rock and ice and frozen gas, obeying physics, indifferent to the questions humans ask of it. Only took 4.5 billion years for us to develop telescopes capable of seeing it, and even now we see only the surface, the light reflected and emitted, the molecules escaping into vacuum. The interior remains hidden, compacted dust and primordial ice, perhaps laced with organic compounds synthesized in the cold, perhaps harbouring molecules more complex than our instruments can detect from this distance. Comets are not simple. They are archives of stellar chemistry, time capsules from epochs when stars were forming in nebulae that have long since dispersed. To study an interstellar comet is to hold, briefly, a sample from another part of the galaxy's ongoing experiment in matter and energy. The fact that 3I Atlas exists at all suggests that interstellar comets are common. For every one we detect, thousands must pass through unnoticed, too faint or too distant or arriving from angles our surveys do not cover. The galaxy, it turns out, is full of wanderers' objects flung from their birth systems, drifting in the space between, occasionally intersecting another star's domain. Our solar system likely ejects comets at a similar rate, sending them outward to become someone else's interstellar visitor, carrying our sun's chemical signature into the dark. It is an exchange, inadvertent and vast, a slow mixing of matter across the galaxy's spiral arms. Only took billions of years to realize we are not isolated, that the boundary between one star system and another is porous, crossed by debris and ice and the patient drift of gravity's influence. Somewhere in the data, in the spectra and light curves and positional measurements, lies a more complete story. But stories require interpretation, and interpretation requires assumptions, and assumptions in astronomy are always provisional. What we know is this 3I Atlas is here, briefly, and it is not from here. The rest is educated inference, models constrained by observation, hypotheses awaiting better data. The comet will not wait for us to finish our questions, for most of its existence. 3I Atlas moves through a darkness unobserved. No telescope tracks its position. No instrument measures its velocity. No astronomer calculates its orbit. The comet simply is drifting through the interstellar medium, untouched by awareness, its presence known only to the physics that govern momentum and gravity. This is the condition of nearly all objects in the universe to exist without witness, to follow trajectories determined by ancient interactions, to cross vast distances in silence. The comet does not announce itself. It does not emit light of its own, save for the faint infrared glow of absorbed starlight re-radiated as heat, and even that is negligible at temperatures barely above absolute zero. The human enterprise of astronomy is recent. A few centuries of systematic observation, a few decades of automated surveys capable of detecting faint-moving objects in the outer solar system. Before that, nothing. Before telescopes, before written records, before human eyes evolved the capacity to wonder at points of light in the night sky. 3 Atlas was already travelling. It passed through regions of space where no intelligence existed to note its passage. It moved past stars that may or may not host planets, past molecular clouds dense with dust, past the bow shocks where stellar winds collide with interstellar gas. All of this occurred without record, without consequence that we can measure. Even within our solar system, there are regions where detection is difficult. The outer reaches beyond Neptune's orbit, beyond the Kuiper belt, into the scattered disk and the Oort cloud are poorly surveyed. Objects there are faint, distant, and slow-moving against the background stars. An interstellar interloper entering from the galactic north or south, passing above or below the plane of planetary orbits, might travel for years through the sun's gravitational influence before crossing a patch of sky monitored by automated surveys. And if the object is small, if it reflects little light, if its trajectory happens to avoid the specific regions of sky being watched on any given night, then it remains invisible, a phantom in the data, present but undetected. Through I, Atlas, likely crossed the heliopause, the boundary where solar wind yields to interstellar plasma sometime in the early 21st century. Though the exact date is uncertain, the heliopause is not a sharp barrier. It undulates, expanding and contracting with the solar cycle, buffeted by the varying pressure of the sun's particle output. Voyager 1 crossed it in 2012 at a distance of about 121 astronomical units from the sun. Voyager 2 followed in 2018 slightly closer. These spacecraft carried instruments to measure the transition plasma detectors, magnetometers, cosmic ray sensors, and they recorded the shift from solar-dominated to interstellar-dominated environment. But they are single points in space, moving along specific trajectories. They cannot monitor the entire boundary. Most of what crosses the heliopause does so without witness. For 3I Atlas, the crossing would have been gradual, imperceptible even to instruments capable of measuring it. The comet has no sensors, no awareness of its environment. The density of particles around it changes fewer protons and electrons from the sun, more neutral hydrogen atoms from the interstellar medium, but this does not affect the comet's trajectory in any meaningful way. Gravity dominates. The sun's pull, though weak at such distances, continues to bend the comet's path inward. The heliopause is a magnetic and plasma boundary, not a gravitational one. Objects pass through it without slowing, without resistance. Their course is determined by mass and velocity and the curvature of space-time around the sun. No one was watching that moment. No observatory had flagged the object yet. It was still too far, too faint, moving through a region of space where sky surveys are sparse and detection algorithms struggle to distinguish real objects from noise. The comet might have been 100 astronomical units from the sun, or 200 when it crossed the heliopause. At such distances, sunlight is extraordinarily dim, roughly 10,000 times fainter than it is at Earth, and reflected light from a small icy body is correspondingly feeble. Even the largest ground-based telescopes would struggle to detect it without knowing exactly where to look. Years pass. The comet continues inward. Its velocity, relative to the sun, is high, perhaps 30 or 40 kilometers per second, depending on the angle of approach. This is faster than objects bound to the solar system typically move, but not absurdly so. The difference is subtle, measurable only through careful tracking over weeks or months. If an astronomer were to observe 3I Atlas for a single night, they might mistake it for a long-period comet, one of the many icy bodies that fall sunward from the Oort cloud, on elliptical orbits lasting thousands or millions of years. Only repeated observations, precise astrometry, and orbital calculations reveal the truth the path is hyperbolic, not elliptical. The comet will not return. During this inward journey, before discovery, the comet remains inert. Its surface temperature is perhaps 30 or 40 Kelvin, too cold for significant outgassing. Water ice does not sublimate at such temperatures. Carbon monoxide, the most volatile common molecule, might release slowly from sun-warmed patches, but the rate is negligible. The comet appears as it has for millions of years, a dark, irregular nucleus, perhaps a few kilometers across. Its surface weathered by cosmic rays and micrometeorite impacts, its interior a mix of ice and dust and organic compounds locked in cold stasis. No coma surrounds it yet, no tailstreams behind. It is invisible not only because it is far, but because it is quiet. Only took a few thousand years to cross from the heliopause to the inner solar system, where detection becomes possible. And even then, the comet must pass through the right patch of sky at the right time, when a telescope is pointed in that direction, when atmospheric conditions are favourable, when the software processing images is sensitive enough to flag faint moving objects. Astronomy is a practice of patience and probability. Most of the sky is not being watched at any given moment. Most objects pass unnoticed. The universe is vast, and our instruments are few. Somewhere in the archives of sky surveys, there may be earlier images of Three-Eye Atlas faint streaks in frames taken weeks or months before formal discovery, overlooked by automated detection algorithms, too dim or too ambiguous to trigger alerts. Researchers sometimes go back after a discovery, searching older data for pre-discovery detections, refining the orbit, extending the observational baseline. Sometimes they find them, sometimes they do not. The comet does not care. It was here, whether we saw it or not. The heliopause is not a place one visits in the ordinary sense. It is transition, a region where the plasma environment shifts character, where the constant outward pressure of the sun's wind meets the incoming flow of interstellar matter and creates a boundary zone measured in astronomical units. The sun releases charged particles, protons, electrons, alpha particles in a continuous stream, accelerated by magnetic activity and coronal heating to speeds of several hundred kilometers per second. This wind expands outward in all directions, carving a cavity in the interstellar medium, a bubble of solar-dominated space called the heliosphere. Beyond this bubble, the galaxy's own plasma flows, thinner but vast, moving with the local standard of rest as stars orbit the galactic center. Where these two environments meet, the physics becomes complex. The solar wind slows, compresses, heats. Magnetic field lines tangle and reconnect. Cosmic rays, high-energy particles accelerated by supernova, and other violent processes find it easier to penetrate inward, no longer deflected as efficiently by the sun's magnetic influence. The exact position of the heliopause shifts over time, responding to the 11-year solar cycle, to variations in solar wind density and speed, to changes in the interstellar medium's pressure. At solar maximum, when the sun is more active, the heliopause pushes outward. At solar minimum, it contracts inward. The motion is slow, a few astronomical units over a decade, but measurable. Three-Eye Atlas crosses this boundary without ceremony. The comet's nucleus is electrically neutral, or nearly so. Its surface may carry a slight charge from solar wind interactions or cosmic ray impacts, but not enough to be significantly affected by magnetic fields. The transition from heliosphere to interstellar space is, for the comet, purely academic. The density of surrounding plasma changes, but the vacuum remains profound by terrestrial standards. A cubic centimetre of space near the heliopause might contain a few dozen particles, compared to trillions in Earth's atmosphere, or the single atom per cubic centimetre of the true interstellar medium. The comet does not feel this difference. It has no sensors, no nervous system, No mechanism to register environmental shifts. It continues along its trajectory, pulled by the sun's gravity, indifferent to the plasma physics unfolding around it. The crossing likely takes years. The heliopause is not a sharp line, but a zone, a gradual shift in conditions spanning several astronomical units. Models suggest the boundary region is turbulent, with features like the heliosheath, the compressed layer of solar wind just inside the heliopause, and the Bauschock, if one exists, where the sun's motion through the interstellar medium creates a shock wave in the surrounding gas. The Voyager spacecraft revealed complexities that earlier models had not predicted. The boundary ripples, shifts, contain substructure. 3I says Atlas passes through all of this at its steady pace, covering an astronomical unit every few weeks, crossing from the interstellar medium into the sun's influence, then deeper, always deeper. As the comet moves inward, the sun's gravity becomes more pronounced. At 200 astronomical units, the gravitational acceleration is minuscule, a tiny fraction of what we experience on Earth's surface, but it is there, constant, cumulative. Over months and years, it bends the comet's path, curving what might have been a straight line through interstellar space into a hyperbola, a trajectory that swings close to the sun, then back outward, never closing into an ellipse. The comet does not slow in any absolute sense. In fact, as it falls deeper into the sun's gravity well, it accelerates, converting gravitational potential energy into kinetic energy, picking up speed as it approaches perihelion. But the acceleration is directed inward, bending the path, and once the comet rounds the sun and begins its outbound journey, gravity will act to slow it again, though never enough to capture it. No telescope tracks this process in real time. The comet is still too far, too faint. It exists in the data only as potential something that must be there, given where it will be discovered later, but not yet seen. Astronomers do not know to look for it. The sky is vast. The number of objects within the solar system is large, and survey resources are finite. Automated programs scan patches of sky repeatedly, searching for motion, for changes, for anything unusual. But they have detection limits. Objects fainter than a certain magnitude simply do not trigger alerts. Objects moving too slowly or too quickly might be filtered out as artifacts or stars. The algorithms are good, but not perfect. During this phase, 3I Atlas is in a state of quantum ambiguity. From a human perspective, it exists, but its existence is not yet confirmed, not yet collapsed into the observable universe by the act of measurement. Philosophically, this is meaningless. The comet's reality does not depend on human observation. Practically, however, it means the comet's history before discovery is reconstructed rather than recorded, inferred from its later trajectory and velocity, extrapolated backward through time using Newton's equations and relativistic corrections. The uncertainty grows with each year we trace backward. Small errors in positional velocity measurements propagate, blurring the comet's past into a cone of possibilities. Only took about a century of modern astronomy to develop the tools needed to detect such objects at all, before photographic plates, before CCD sensors, before automated sky surveys and digital image processing. An interstellar comet could have passed through the inner solar system entirely unnoticed, visible perhaps to the naked eye if it developed a bright coma, but unrecognized as alien, catalogued if catalogued at all as merely another comet, its hyperbolic orbit attributed to measurement error or insufficient observational baseline. How many came and went before we had the means to know them? The question is unanswerable. The past is silent on objects no one recorded. The heliopause, meanwhile, continues its slow breathing, expanding and contracting with the solar wind's rhythm, indifferent to what crosses it. Plasma flows, magnetic fields shift, cosmic rays spiral through the boundary region. The sun burns through its hydrogen, converting mass to energy, flooding space with light and particles, maintaining the bubble that defines its domain. and within that domain, growing brighter with each passing month, 3I Atlas falls sunward, still unseen, still unknown, carrying its ancient chemistry toward the moment of discovery. The warming begins so gradually that no single moment marks its start. Sunlight, faint at first, falls upon the comet's surface photons travelling 8 minutes from the sun's core where they were born in fusion, then scattered through the radiative zone for thousands of years, finally released into space to cross the solar system unimpeded. At 100 astronomical units, this light delivers perhaps 1/10,000th the energy that reaches Earth. The surface temperature of 3I Atlas rises from 30 Kelvin to 35, then 40. The change is measurable, if anyone were measuring, but the effects remain subtle. Ice does not melt at 40 Kelvin. Water remains locked in crystalline structure. Molecules bound in hexagonal lattice, motionless save for quantum vibrations. But the comet is not pure water ice. Embedded within the matrix are more volatile compounds: carbon monoxide, carbon dioxide, methane, nitrogen. These molecules have lower sublimation points, temperatures at which they transition directly from solid to gas without passing through a liquid phase. Carbon monoxide, the most volatile, begins to sublimate around 25 Kelvin. Though the rate at such temperatures is extraordinarily slow, a few molecules per square centimetre per second, barely detectable. As the comet warms, the rate increases exponentially. At 45 Kelvin, the sublimation accelerates. At 50, it becomes measurable. At 60, gas begins to stream from the surface in quantities sufficient to carry dust particles with it. This is not a dramatic process. There are no geysers, no explosive eruptions. The gas seeps outward, molecule by molecule, diffusing into the vacuum. The pressure at the comet's surface is negligible by human standards, perhaps a billionth of Earth's atmospheric pressure, but it is enough. Dust grains, loosely bound to the surface by weak van der Waals, forces and the faint gravity of the nucleus, lift free. They are small. These grains, typically a fraction of a micron to a few microns across smaller than the width of a human hair, comparable to smoke particles or bacterial cells, composed of silicate minerals, organic compounds, perhaps carbonaceous material darkened by cosmic ray processing. They scatter sunlight, making the comet visible in a way the nucleus alone never could. The coma begins to form. This word coma derives from the Greek for hair, a reference to the fuzzy appearance comets present in telescopes. It is an atmosphere of sorts, though not gravitationally bound. The gas and dust expelled from the nucleus expand outward, driven by their own thermal velocities and by radiation pressure from sunlight. Over weeks, the coma grows from a few hundred kilometers across to several thousand, eventually perhaps 10,000 or more, larger than Earth, though far more tenuous. The density is so low that the coma is effectively transparent. Light passes through with minimal absorption, yet the sheer volume means that enough photons scatter to make the entire structure glow. Water ice begins to contribute, though it remains a minor component at distances beyond 5 or 6 astronomical units from the Sun. Water requires more energy to sublimate than carbon monoxide or carbon dioxide. Its sublimation temperature, the point at which the rate becomes significant, is around 150 Kelvin, which the comet's surface reaches only when much closer to the Sun. For now, water remains locked within the nucleus, a frozen reservoir awaiting warmth. The coma is dominated by more volatile species, the molecules that escape first, creating a chemistry that reflects the comet's outer layers rather than its deep interior. Instruments on Earth, if pointed at the right patch of sky, could detect this brightening, this transition from inert object to active comet. But 3I Atlas is still far, still faint. The coma, though large in physical size, is dim, spread across an area that dilutes its surface brightness. A human observer with a backyard telescope would see nothing. Even professional observatories, unless specifically targeting the comet's position, would likely overlook it. The sky is crowded with faint smudges, distant galaxies, nebulae, asteroids, background stars rendered fuzzy by atmospheric turbulence, one more faint glow among thousands. The outgassing is asymmetric. The sun's light does not heat the nucleus uniformly. The side facing the sun receives direct illumination. The side in shadow remains colder. This creates temperature gradients across the surface, and where temperature varies, sublimation rates vary. More gas escapes from the sunlit hemisphere than from the night side. This asymmetry exerts a tiny force on the nucleus, a rocket effect, though minuscule compared to the sun's gravity. Over time, over many orbits, if the comet were on a bound orbit, this non-gravitational force could alter the trajectory measurably. But 3I Atlas is not bound. It will pass through once, and the rocket effect, while real, is negligible in the context of its hyperbolic path. Rotation complicates the picture. The nucleus spins, its rotational period perhaps a few hours or a few dozen hours, depending on its shape and formation history. As it spins, different regions face the sun, warming and cooling in rhythm. The outgassing waxes and wanes, creating temporal variations in coma brightness and gas production rate. If astronomers were monitoring closely, they could detect these variations, using them to infer the rotation period, the shape of the nucleus, perhaps even the distribution of volatile material across the surface. But no one is monitoring yet. The data exists, in principle, in photons scattered and emitted, but it is not being collected. The comet warms and rotates and outgasses in solitude. Only took a few million years of interstellar cold to reach this point, and now, within a few years of sunlight, the surface chemistry begins to change. Molecules that have sat frozen since the comet's formation, or since its last close passage to a star, if such a passage occurred now, sublimate, breaking free, carrying with them information about ancient processes, about temperatures and pressures in a protoplanetary disk light years away and billions of years ago. The comet is awakening, though it has no consciousness, no intent. It is simply responding to energy input, to photons absorbed and re-emitted, to thermodynamics playing out across ice and dust. The interior remains cold. Heat diffuses slowly through ice and porous dust, even as the surface warms to 70 or 80 Kelvin, a meter below. The temperature might still be 40 or 50. The nucleus is insulating itself, the outer layers of dust and sublimated ice residue forming a lag deposit that shields the interior from solar radiation. This lag deposit darkened, enriched in non-volatile material, reduces the albedo, making the surface absorb more sunlight, but it also reduces the rate at which heat penetrates inward. The comet's thermal evolution is a balance between these effects, a slow process that will continue as long as sunlight provides energy. The coma is a cloud of molecules escaping bondage. Water vapor, though still minor in the outer solar system, rises with carbon monoxide, carbon dioxide, and traces of more complex organics: methanol, formaldehyde, hydrogen cyanide, cyanogen. Each species carries away kinetic energy, each photon of absorbed sunlight converted into molecular motion, into the vibrational and rotational states that quantum mechanics permits. The gas expands radially from the nucleus, cooling as it spreads, the temperature dropping even as the molecules move outward at velocities of a few hundred meters per second. In the vacuum of space, there is no air resistance, no friction to slow them. They simply travel until they are ionized by solar ultraviolet radiation, or dissociated by photons energetic enough to break molecular bonds, or until they drift so far that they are no longer associated with the comet at all. Spectroscopy reads this chemistry. Light from the sun passes through the coma, and molecules absorb specific wavelengths corresponding to electronic, vibrational, or rotational transitions. The absorbed light leaves gaps in the spectrum, dark lines at precise wavelengths, fingerprints unique to each molecular species. Alternatively, molecules excited by solar radiation re-emit light at characteristic wavelengths, producing emission lines. By observing the comet through a spectrograph, an instrument that disperses light into its component colours, astronomers can identify which molecules are present, estimate their abundances, and measure their velocities through Doppler shifts. The process is indirect, inferential, but remarkably precise. A single emission line can reveal not only the molecule's identity but also its temperature, density, and motion. Water vapour, when it appears in significant quantities, produces strong emission in the ultraviolet and infrared. The hydroxyl radical OH, a fragment of water molecules broken apart by solar UV, emits at 308 nanometers, a wavelength observable from the ground if atmospheric conditions permit. This emission is often one of the brightest features in a comet's spectrum, a proxy for water production rate. By measuring the intensity of the OH emission and applying models for how water dissociates and how OH distributes through the coma, researchers calculate how much water ice is sublimating per second. For an active comet near perihelion, this can be thousands of kilograms per second, or more. For 3I Atlas, still distant, the rate is lower, but measurable. Carbon monoxide emits in the ultraviolet as well, though detection often requires space-based telescopes. As Earth's atmosphere absorbs much of the UV spectrum, the molecule is simple two atoms bound by a triple bond, but its presence is diagnostic. CO sublimates at low temperatures, so its detection indicates either that the comet is intrinsically rich in carbon monoxide, or that it has recently arrived from the cold outer regions where CO does not easily escape. In interstellar comets, the CO abundance is of particular interest, as it may differ from solar system comets, reflecting different formation conditions or evolutionary histories. If 3I Atlas shows unusually high or low CO relative to water, that anomaly becomes a clue, a constraint on models of its origin. Cyanogen, a molecule composed of 2 carbon atoms and 2 nitrogen atoms, bonded in a linear chain, appears as well. Its emission lines fall in the visible spectrum, accessible to ground-based observers. Cyanogen is mildly toxic, notorious in earlier centuries for causing public alarm when Earth passed through the tail of Halley's Comet in 1910. Newspapers warned of poisonous gas, though the density in a cometary tail is so low that it poses no threat. The panic was unfounded, but the chemistry was real. Cyanogen's presence in comets speaks to the carbon and nitrogen chemistry in protoplanetary disks, to the processes that incorporate these elements into icy grains, to the temperatures at which such molecules condense from gas to solid. Methanol, CH3OH, is more complex. A simple alcohol, a molecule of 1 carbon, 4 hydrogen and 1 oxygen, it forms in cold environments, on the surfaces of dust grains in molecular clouds, where hydrogen atoms stick and react with carbon monoxide ice to build more elaborate structures. Methanol sublimates at intermediate temperatures, between the volatility of CO and the stubbornness of water ice. Its presence suggests that the comet's ices formed in a cold, dense environment, where surface chemistry on grains could proceed over long timescales. Detecting methanol in 3I Atlas would indicate that such conditions existed in its birth system, that the processes active in our own solar nebula are not unique, that molecular complexity arises wherever the right ingredients and conditions coincide. Each molecule has a story, though the story is written in quantum transitions and thermodynamic constraints rather than narrative prose. The abundances are ratios, percentages, numbers that constrain models. If carbon monoxide comprises 10% of the coma's gas by number, and water comprises 60%, and carbon dioxide 20%, and methanol 1%, then these ratios reflect the nucleus composition, the thermal history, the balance of volatiles that survived the comet's formation and its millions of years in interstellar space. Variations from one comet to another, or between interstellar and solar system comets, hint at the diversity of planetary system chemistries, at how small differences in initial conditions propagate into measurable outcomes. The mystery lies in what is missing, or present in unexpected amounts. Perhaps 3I Atlas shows an overabundance of some molecule rare in solar system comets, or a deficit of something common. Perhaps the isotope ratios are subtly wrong, the deuterium enrichment higher or lower than models predict for our region of the galaxy. These anomalies, if they exist, are the most interesting findings, the ones that challenge assumptions, that force revisions to theories of how and where comets form, but they require careful measurement, repeated observations, cross-checks against instrumental calibration and atmospheric interference. Spectroscopy is powerful, but also delicate, vulnerable to noise and systematic error. Only took 100 years of quantum mechanics to develop the tools to interpret these spectra correctly. Before the early 20th century, before scientists understood atomic and molecular structure, absorption and emission lines were mysteries, patterns in starlight with no clear explanation. Now, each line is a known quantity, a transition between energy states calculated from first principles and confirmed in laboratory experiments. The universe is readable, its chemistry accessible through light, through the interaction of photons and matter, through the precision of modern instrumentation and the patience of observers who collect photons one by one, building spectra from faint signals accumulated over hours or nights. The coma continues to grow. Gas and dust stream outward, the production rate increasing as the comet moves deeper into the sun's warmth. Somewhere in that expanding cloud, molecules collide, react, form new species not present in the original ice. Somewhere, solar wind ions impact the coma, ionizing neutrals, creating a plasma component that glows faintly in different wavelengths. The chemistry is dynamic, evolving, a far from equilibrium system driven by solar energy, and through it all, light carries information outward, toward Earth, toward telescopes, toward the instruments that will read the story written in wavelengths and intensities. The trajectory is hyperbolic, a term from mathematics describing a curve that opens indefinitely, that does not close upon itself. In orbital mechanics, this shape signifies escape. An object on a hyperbolic orbit moves faster than the local escape velocity at every point along its path. Gravity pulls, bends the trajectory, but cannot capture. The orbit curves sharply as the object approaches the Sun, swings around perihelion, then curves outward again, asymptotically approaching a straight line at infinite distance. The eccentricity a number describing orbital shape exceeds 1. Circles have eccentricity 0, ellipses between 0 and 1, parabolas exactly 1, hyperbolas greater than 1. For 3i Atlas, the eccentricity is perhaps 1.2 or 1, 5 or higher, depending on precise measurements still being refined. This number means everything. It separates the transient from the permanent, the visitor from the resident. Objects bound to the solar system travel on ellipses, their eccentricities less than 1, their fates tied to the sun's gravity. They may venture far long-period comets reach thousands of astronomical units at aphelion, but they always return. Their orbits closing over millennia or millions of years. Hyperbolic objects do not return. They pass through once, influenced by the sun's gravity but not captured by it, and then they leave, continuing their journey through the galaxy. The distinction is absolute, determined by velocity and distance, by the balance between kinetic energy and gravitational potential energy. Astronomers calculate the orbit from position measurements. Observations on different nights provide points along the comet's path, right ascension and declination, sky coordinates that translate to three-dimensional space once distance is factored in. The more observations, the better the orbit determination, with only a few points. The uncertainty is large. The comet might be on a highly eccentric ellipse or a shallow hyperbola, and the data cannot yet distinguish between them. But with weeks or months of tracking, the ambiguity resolves. The best fit orbit emerges from statistical analysis, a curve through phase space that minimizes the residuals between predicted and observed positions. Software performs these calculations, iterating through possible orbits, adjusting parameters, seeking convergence. The process is deterministic given the positions and times. Newton's laws and Kepler's equations dictate the orbit, but the real world introduces noise. Atmospheric turbulence blurs images, reducing positional accuracy. Timing errors, catalogue uncertainties, instrumental drift all contribute small errors that propagate through the calculation. The result is an orbit with uncertainties, error bars on each parameter. The eccentricity is not a single number, but a probability distribution, most likely around some central value, less likely at the extremes. For 3i Atlas, that distribution peaks above 1. The hyperbola is real. The orbit's orientation in space matters as well. The comet does not travel in the plane of the planet's orbits, the ecliptic, but enters from above or below, inclined at some angle. The ascending node, the point where the orbit crosses the ecliptic from south to north, and the argument of perihelion, the angle from that node to the closest approach, define the orbit's geometry. Together with the semi-major axis, eccentricity, and time of perihelion passage, these elements fully specify the trajectory. They are the language in which astronomers describe motion, a compact notation encoding vast distances and velocities into a handful of numbers. Predicting where the comet will be at any future or past time becomes straightforward once the orbit is known. Plug the desired date into the equations, solve for position and velocity, and the comet's location emerges. This is how astronomers plan observations, how they determine when the comet will be brightest or best positioned for study, how they look backward to check archival images for prediscovery detections. The orbit is a map, a description of the comet's path through four-dimensional space-time, and like all maps, it simplifies reality. Perturbations from planets, non-gravitational forces from outgassing, even relativistic corrections slightly alter the trajectory. But for most purposes, the Keplerian orbit suffices. The hyperbolic nature of the orbit tells another story. It constrains where the comet came from. By tracing the trajectory backward, away from the Sun, astronomers can determine the comet's velocity and direction at very large distances, where the Sun's gravity is negligible and the motion approximates a straight line. This asymptotic velocity vector, combined with the Sun's own motion through the galaxy, allows calculation of the comet's velocity relative to the local standard of rest, the average motion of stars in the solar neighbourhood. If that velocity is low, the comet may have originated from a nearby star, relatively recently ejected and not yet dispersed into the general galactic population. If high, the comet has been wandering longer, its origin more distant or more ancient. For 3i Atlas, the velocity relative to the local standard of rest is moderate, a few tens of kilometers per second, consistent with an object that has orbited the galaxy several times, gradually randomized in direction by gravitational interactions with molecular clouds and spiral arm passages. This does not pinpoint a specific origin, but it rules out certain scenarios. The comet is not freshly ejected from a star just light years away. If it were, the velocity would likely be lower, the trajectory more clearly pointing back to a specific source. Instead, 3i Atlas is a member of the general interstellar population, a wanderer whose origins are obscured by time and distance. Only took 400 years of orbital mechanics, from Kepler's laws to modern numerical integrators, to understand trajectories with this precision. Before Kepler, before Newton, comets were atmospheric phenomena, exhalations from the Earth, portents of disaster, objects without clear physical explanation. The idea that they follow predictable paths, governed by the same gravity that holds planets in their courses, was revolutionary. And the recognition that some of those paths are unbound, that comets can come from beyond, required precise measurements, careful data reduction, the accumulation of observations across decades and centuries. Now, it is routine. A dozen measurements, a few weeks of data, and the orbit is known to within small uncertainties. The hyperbola revealed, the visitor identified. The comet does not know it is hyperbolic. It follows its path because gravity dictates it, because momentum carries it forward, because no force acts to close the orbit into an ellipse. The distinction between bound and unbound is human categorization, useful for prediction and understanding, but not a feature the comet itself experiences. It simply moves, tracing the curve that physics requires, indifferent to whether that curve will bring it back or send it away forever. Light passing through the coma carries information encoded in wavelengths. When sunlight, already a mixture of all visible colours plus ultraviolet and infrared, encounters molecules in the expanding gas cloud, specific wavelengths are absorbed. An electron in a cyanogen molecule, for instance, can jump from a lower energy orbital to a higher one if it absorbs a photon of precisely the right energy. The photon disappears from the beam of sunlight passing through. When that light is dispersed by a spectrograph into its component wavelengths, a dark line appears at the position corresponding to the absorbed photon's energy. This is an absorption line. Conversely, when an excited molecule returns to a lower energy state, it emits a photon at a specific wavelength, creating an emission line, a bright feature in the spectrum. The pattern of these lines is unique to each molecule. Cyanogen has its set of transitions, carbon monoxide another, water vapour another. By matching observed lines to laboratory measurements and quantum mechanical calculations, astronomers identify which molecules are present. The intensity of each line relates to the molecule's abundance and temperature. Stronger lines mean more molecules, or molecules at higher excitation states, or both. The width of the lines reveals velocity molecules moving toward Earth produce Doppler-shifted lines at slightly shorter wavelengths. Molecules moving away at slightly longer wavelengths. The coma expands radially, so half the molecules move toward us, half away, and the result is a broadened line, its width proportional to the expansion velocity. Isotope ratios emerge from careful analysis. Deuterium, the heavy isotope of hydrogen, forms water molecules slightly different from normal H2O. The mass difference shifts the wavelengths of molecular transitions by small but measurable amounts. If the comet's water contains more deuterium than expected, the spectrum shows a faint secondary set of lines offset from the main water features. Detecting this requires high spectral resolution and long exposure times, but it is possible. The ratio of deuterium to hydrogen in water, often written as DH, varies, depending on where and how the water formed. In our solar system, comets typically show DH ratios a few times higher than Earth's ocean water, suggesting their ice formed in colder regions of the protoplanetary disk or incorporated material from the interstellar medium. If 3I Atlas shows a different ratio, that difference constrains models of its origin. Carbon isotopes matter as well. Carbon-13 is rare compared to carbon-12, making up about 1% of carbon in the solar system. But this ratio is not universal. Stars of different masses and evolutionary stages produce carbon isotopes in different proportions through nucleosynthesis. When those stars die and release their processed material into the galaxy, they enrich the interstellar medium with specific isotopic mixtures. A comet forming in a region recently enriched by supernova ejecta might have a different carbon-13 abundance than one forming in a quieter, less processed part of the galaxy. Measuring this requires isolating spectral lines from molecules containing carbon-carbon monoxide, carbon dioxide, methane, and resolving the faint signatures of the heavier isotope. The observations are difficult, the signal's weak, but the potential payoff is significant, a direct measurement of nucleosynthetic history recorded in ice. Nitrogen isotopes add another layer. Nitrogen-15 is even rarer than carbon-13, comprising less than 0.5% of nitrogen. Its abundance depends on conditions in the molecular cloud where the comet's parent star formed, on the degree to which previous generations of stars processed and returned material to the interstellar medium. Cyanogen, hydrogen cyanide, and ammonia all contain nitrogen and can be used to measure the nitrogen-14 to nitrogen-15 ratio. If the ratio differs from solar system values, it hints at a different galactic neighbourhood, different chemical enrichment history, perhaps even a different epoch in the galaxy's evolution. The galaxy has changed over billions of years as successive generations of stars have lived and died, gradually increasing the abundance of heavy elements. A comet formed 6 billion years ago might show isotopic signatures distinct from one formed 4 billion years ago. These measurements push the limits of current instrumentation. The comet is faint, the spectral lines weak, the differences between isotopes subtle. Observing time on large telescopes is competitive, allocated in units of hours or nights, never enough to answer every question. Atmospheric interference water vapour in Earth's atmosphere absorbing the same wavelengths as cometary water. Oxygen absorbing UV light complicates the analysis. Space-based telescopes avoid atmospheric problems but are even more constrained in availability. The Hubble Space Telescope, the James Webb Space Telescope, these are shared resources, scheduled months or years in advance, with thousands of proposals competing for observation time. An interstellar comet, arriving unannounced, disrupts the schedule. Astronomers scramble to request directors' discretionary time, arguing that the opportunity is fleeting, that the comet will not return, that the science is urgent. Sometimes they succeed, sometimes they do not. The data that does arrive is often preliminary. A single night's observation might provide a rough spectrum, enough to identify major molecular species but not detailed abundances or isotope ratios. Follow-up observations refine the picture. Multiple telescopes, different instruments, various wavelengths, each adds a piece to the puzzle. Ultraviolet observations from space capture carbon monoxide and hydroxyl. Infrared observations from ground-based telescopes probe water vapor and organic molecules. Visible light spectroscopy measures cyanogen and ionized species. Radio observations detect carbon monoxide and methanol with high precision. Together, these create a multi-wavelength portrait, a chemical inventory of the comet's coma. Uncertainties remain. Some molecules are present but undetectable with current methods, either because their spectral lines fall in inaccessible wavelengths or because their abundances are too low. Some features in the spectrum resist interpretation: unidentified lines that do not match any known molecule, or lines that appear where they should not, suggesting unexpected chemistry or unknown species. The models used to convert observed spectra into molecular abundances make assumptions about temperature, density, radiation field, collisional excitation rates, and those assumptions may not perfectly match the real conditions in the coma. The derived abundances have error bars, sometimes large, sometimes so large that the measurement becomes a constraint rather than a value the molecule is present, but the amount is uncertain. Only took a century of spectroscopy, from the first prism experiments to modern high-resolution Echelle spectrographs, to reach this level of sophistication, and still, gaps remain. The comet's interior is unknown. The spectrum reveals only what escapes, only the molecules that reach the coma and interact with light. Deeper within the nucleus, other ices may hide species that do not sublimate at the comet's current temperature, or that are trapped beneath layers of dust and refractory material, sealed away from sunlight. These hidden reservoirs will remain unknown unless the comet approaches closer, warms more, releases them. And even then, what escapes is only a sample, not the whole. The nucleus itself remains invisible, buried within the growing coma. To see it directly would require resolving an object a few kilometers across at a distance of several astronomical units, an angular size so small that even the largest telescopes cannot distinguish it from a point source. What astronomers observe is the integrated light from the entire coma, a diffuse glow spread across thousands of kilometers, with the nucleus contributing only a tiny fraction of the total brightness. Models attempt to infer the nucleus properties from indirect evidence. The rate of gas production suggests a surface area, which combined with assumptions about shape yields and estimated size. The amount of dust in the coma, measured by scattered sunlight, constrains the dust-to-gas ratio, which in turn hints at the nucleus composition and structure. Size estimates are uncertain. If the nucleus is spherical, and if the surface is uniformly active, and if the gas production rate is known, then the diameter can be calculated. But none of these assumptions is likely to be true. Real cometary nuclei are irregular, potato-shaped or bilobed, their surfaces pockmarked with craters and scarred by sublimation pits. Activity concentrates in certain regions, perhaps where fresh ice is exposed, or where sunlight strikes at favourable angles while other areas remain dormant, covered in dust-lag deposits that insulate the interior. The gas production rate varies with time, with rotation, with distance from the sun. Observations capture only snapshots, moments in a dynamic process, and extrapolating from those moments to global properties requires assumptions that may or may not hold. Perhaps the nucleus is 3 kilometers across, perhaps 5, perhaps only 1, a small body made to appear significant by vigorous outgassing. The density is unknown. Comets visited by spacecraft have shown densities far below that of solid ice, around 400 to 600 kilograms per cubic meter, compared to 900 for pure water ice, indicating that the nuclei are porous, loosely bound aggregates of ice and dust with voids comprising half or more of the volume. This porosity affects thermal conductivity, affecting how heat penetrates the interior, affecting sublimation rates, affecting everything. But without a spacecraft mission, porosity is a guess, an inference based on analogy to other comets and theoretical models of comet formation. The surface is likely dark. Observations of cometary nuclei by visiting spacecraft have revealed albedos reflectivity around 3 to 6%, darker than charcoal, darker than asphalt. This darkness comes from organic compounds, complex carbon-rich molecules built up over time from simpler precursors through radiation chemistry and thermal processing. The surface layer, exposed to cosmic rays and a solar wind during the comet's long journey, has been chemically altered, polymerized into tars and kerogens that absorb rather than reflect light. Beneath this dark crust, the ice remains bright, but it is shielded, hidden, contributing to the comet's appearance only when sublimation breaks through the crust and exposes fresh material. Rotation complicates the thermal environment. As the nucleus spins, each patch of surface experiences cycles of heating and cooling. On the sunlit side, temperatures rise, sublimation accelerates, gas and dust escape. On the night side, temperatures plummet, sublimation halts, the surface refreezes any vapour that has not escaped. The rotation period, perhaps hours, perhaps days, sets the timescale for these cycles. A fast-spinning nucleus experiences rapid thermal cycling, with little time for heat to penetrate deeply before the surface rotates into shadow. A slow rotator allows more heat to diffuse inward, potentially warming subsurface layers to the point where deeper ice begins to sublimate, contributing to gas production even on the night side through diffusion of gas through the porous matrix. Shape affects stability. An elongated nucleus, spinning end over end, experiences centrifugal forces that vary across its surface. If the rotation is too fast, these forces can overcome the weak self-gravity and tensile strength of the loosely bound material, causing the nucleus to shed fragments, or even disrupt entirely. Comet nuclei have been observed to break apart, sometimes triggered by rotational instability, sometimes by thermal stress, sometimes for reasons not fully understood. Whether 3I Atlas is stable depends on its shape, rotation rate, internal strength, all unknowns, all inferred only from statistical tendencies and analogy to other comets. The mystery deepens when considering what lies within. The interior of the nucleus has never been warmed by the sun, at least not during this passage. If the comet formed billions of years ago and has spent most of its existence in the cold interstellar medium, the core temperature might be only a few Kelvin, cold enough that even hydrogen would be solid, though hydrogen is unlikely to be present in significant amounts. More realistically, the interior is at temperatures set by the ambient radiation field of the galaxy microwave background radiation, starlight from distant suns, cosmic rays perhaps 10 to 20 Kelvin. At such temperatures, nearly all volatiles are frozen. Carbon monoxide, nitrogen, methane all solid. Water, of course, solid. Only helium and hydrogen remain gaseous, and these are too light to be retained by the comet's feeble gravity. Within this frozen matrix, complex organic molecules may reside, amino acids, perhaps, though their detection in comets is contested and difficult, polycyclic aromatic hydrocarbons, common in the interstellar medium and detected in cometary dust, formaldehyde, methanol, formic acid, simple molecules that form on dust-grained surfaces in molecular clouds. The inventory is potentially rich, a record of prebiotic chemistry, of the molecular building blocks that might eventually contribute to life if delivered to suitable environments. But without a sample return mission, without direct analysis in a laboratory, the exact composition remains speculative, constrained by remote spectroscopy and models. Only took a few close encounters with comets, Halley, Borrelly. Wild, 2 Tempel 1 Hartley 2, Churyumov-Gerasimenko for spacecraft to reveal how little we understood from ground-based observations alone. Each mission surprised. Each nucleus was darker, more irregular, more geologically complex than expected. Jets erupted from specific locations, not uniformly across the surface. Smooth plains bordered rough terrain. Layering suggested formation by accretion rather than monolithic collapse. The diversity was striking, each comet an individual, not merely an instance of a universal template. And yet, all those missions visited solar system comets, objects that have orbited the Sun for billions of years. An interstellar comet might be even more alien, its nucleus shaped by different processes, its surface weathered by a different radiation environment, its interior preserving chemistry from another star's disk. 3i Atlas keeps its secrets. The coma grows, the gas production increases, the spectral lines brighten, but the nucleus remains hidden, a phantom presence inferred from the cloud it creates, known only through the evidence of its activity. Direct imaging would require a spacecraft, a mission planned and launched with years of lead time. Impossible to arrange for an object discovered only months before its passage. The opportunity slips away. The comet will round the Sun, drift outward, fade, and disappear, and the nucleus will never be seen. Perihelion approaches, the point of closest passage to the Sun. For 3i Atlas, this distance is measured in astronomical units, perhaps 1.5, perhaps 2, perhaps closer. The exact value depends on the orbit's geometry, on the specific trajectory the comet follows through the inner solar system. At perihelion, the comet will be moving fastest, gravitational acceleration at its maximum, the Sun's light most intense. This is the moment of peak activity, when gas production reaches its highest rate, when the coma glows brightest, when observers on Earth have their best opportunity to study the chemistry and structure of this visitor from interstellar space. The approach is gradual, measurable in weeks and months rather than days. Each day, the comet moves slightly closer. Each day, the solar flux increases, the surface temperature rises, the sublimation rate accelerates. Water ice, dormant at distances beyond 5 astronomical units, begins to contribute meaningfully to the gas production at 3 astronomical units. Water becomes the dominant volatile, outpacing carbon monoxide and carbon dioxide. At 2 astronomical units, the water production rate may reach hundreds of kilograms per second. At perihelion, perhaps a ton per second, though the exact rate depends on the nucleus size, the active fraction of the surface, the efficiency with which heat penetrates to subsurface ice. The comet does not experience this as acceleration in the human sense. There is no sensation, no awareness, no internal clock measuring the passage of time. The nucleus warms because photons strike its surface, because molecules absorb energy and transition to higher vibrational states, because heat diffuses inward through thermal conductivity. The process is deterministic. governed by thermodynamics, by the Stefan Boltzmann law relating temperature to radiated energy, by the sublimation curves of various ice species. At equilibrium, the energy absorbed from sunlight balances the energy lost through radiation and sublimation. But equilibrium is never quite achieved, because the comet is moving, because the solar flux is changing, because rotation brings new surfaces into sunlight before the old ones reach steady state. Observations intensify. Telescopes around the world track 3-eye atlas, allocating time from already crowded schedules. Northern Hemisphere observers catch it in the evening sky, Southern Hemisphere observers in the morning, the geometry shifting as the comet moves along its orbit. Photometry measures brightness over time, constructing a light curve that reveals rotation periods and activity variations. Spectroscopy captures high-resolution spectra, refining molecular abundances and searching for rare species. Imaging attempts to resolve the coma structure, looking for jets or asymmetries that might indicate localized outgassing regions on the nucleus. The data arrives in fragments, each observation adding a small piece to the larger picture. One telescope measures the production rate of carbon monoxide, another captures infrared spectra showing water vapor and dust. A third monitors the coma's expansion velocity through Doppler line widths. Coordinating these observations is challenging. Telescopes have different capabilities, different schedules, different weather conditions. A planned observation might be cancelled by clouds, or compromised by moonlight, or delayed by instrument malfunction. The dataset becomes patchy, incomplete, better in some wavelengths and parameters than others. Still, patterns emerge. The gas production rate shows a smooth increase as the comet approaches perihelion, consistent with models of increasing solar illumination and rising surface temperature. Superimposed on this trend are shorter period variations, likely due to rotation bringing more or less active regions into sunlight. The amplitude of these variations suggests that activity is not uniform, that some areas of the nucleus outgas more vigorously than others. The exact rotation period is difficult to determine, perhaps 8 hours, perhaps 12. The signal noisy and the data gaps problematic. Multiple periods might be present if the nucleus is tumbling rather than rotating around a single axis. Dust production correlates with gas production, as expected. Dust grains, lifted from the surface by escaping gas, scatter sunlight and contribute to the coma's brightness at visible wavelengths. The dust-to-gas mass ratio, a parameter describing how much solid material is released relative to volatile gas, appears to be around 1, meaning roughly equal masses of dust and gas escape. This is typical for comets, though individual objects show wide variation. The dust itself is not homogeneous. Grain sizes range from sub-micron particles to millimeter-sized chunks. Composition varies as well. Silicate minerals, organic compounds, perhaps metallic inclusions, spectroscopy of the dust, using infrared wavelengths where silicate features appear, suggests a mix of crystalline and amorphous materials consistent with processing in a protoplanetary disk. The coma extends outward, now perhaps 50,000 kilometers across, larger than Jupiter, though still far more tenuous. The gas density at the nucleus surface might be 1 trillion molecules per cubic centimeter, high by space standards but a hard vacuum by terrestrial measure. As the gas expands outward, the density drops inversely with distance squared. At 10,000 kilometers from the nucleus, the density is 1 billion molecules per cubic centimeter. At 50,000 kilometers, 10 million. The coma is transparent, effectively invisible except for the light scattered by dust and emitted by excited molecules. It is structure without solidity, presence without substance. The closest approach to the Sun lasts only hours in the sense of when the comet is nearest, but the period of peak activity spans days or weeks. Perihelion is not an instantaneous event, but a passage, a time when the orbit brings the comet to minimum distance. The moment itself is defined by geometry, calculable from the orbital elements, precise to within seconds if the orbit is well determined. But the physical consequences, the maximum temperature, the peak sublimation rate may lag slightly, as the nucleus thermal inertia delays the response to changing solar illumination. Only took billions of years to reach this moment, this brief interval when an ancient object from another star system swings close enough to ours to be studied, and the moment is fleeting. Within weeks, the comet will begin its outbound journey, the solar flux decreasing, the activity declining, the opportunity narrowing. There is urgency in the observations, a recognition that every night of data matters, that clouds or equipment failure could mean lost chances. The comet will not return. If the measurements are not made now, they will never be made. The sun itself is indifferent, a sphere of fusing hydrogen, radiating energy into space without preference or awareness. It has hosted countless comets, both from its own reservoir and from interstellar space, and it will host countless more. The passage of 3 Atlas is unremarkable on stellar timescales. A mote of ice and dust briefly warmed before returning to cold, but for those watching, measuring, interpreting, the passage is unique, a singular opportunity to glimpse chemistry from another star, to test models of planetary system formation against data from beyond our own, to add one more data point to the sparse catalogue of interstellar visitors. The tail begins to form, though not as a single structure but as 2 distinct phenomena, each governed by different physics, each pointing away from the sun but along different trajectories. The dust tail is the more prominent to the eye, composed of solid particles that have escaped the nucleus and now orbit the sun independently, though their paths remain influenced by the comet's original motion. These particles, ranging from microns to millimeters in size, reflect sunlight efficiently, creating a broad, curved arc that trails behind the comet in its orbit. The curvature arises because larger particles, less affected by radiation pressure, follow more tightly curved orbits closer to the comet's original path, while smaller particles are pushed more strongly outward, creating a swept-back appearance. Radiation pressure is the force responsible for this sweeping. Photons carry momentum, and when they strike a dust particle and are absorbed or reflected, they transfer that momentum to the particle. The force is small, on the order of piconewtons for a micron-sized grain, but in the absence of air resistance, it is cumulative and persistent. Over days and weeks, this gentle push accelerates the dust outward from the sun, creating a tail that can extend millions of kilometers, visible from Earth as a faint golden or yellowish glow, the color reflecting the sun's own spectrum scattered by the dust. The tail does not stream behind the comet in the direction of motion, as intuition might suggest, but rather points away from the sun, regardless of whether the comet is approaching or receding. This peculiarity puzzled early astronomers, resolved only when the nature of radiation pressure was understood. The ion tail is different, composed of ionized gas rather than solid particles, molecules in the coma carbon monoxide, water vapor. Cyanogen are struck by solar ultraviolet photons energetic enough to remove an electron, creating positively charged ions. These ions interact with the solar magnetic field, carried outward by the solar wind at speeds of several hundred kilometers per second. The ion tail is typically straight, pointing almost exactly away from the sun, and glows with a blue or bluish-white light due to fluorescence from ionized carbon monoxide and other molecular ions. The tail can be narrow, stretching across vast distances, sometimes showing structure knots, disconnection events, waves due to interactions with the variable solar wind and magnetic field. Disconnection events occur when the magnetic field embedded in the solar wind changes polarity, severing the magnetic connection between the comet's ionosphere and the solar wind. The ion tail is literally cut off, drifting away as a detached structure, while a new tail begins to form from fresh ions in the coma. These events are dramatic when captured in time-lapse images, the comet appearing to lose and regrow its tail over hours or days. They reveal the dynamic nature of the solar wind. The fact that space near the Sun is not static but filled with plasma flows, magnetic turbulence, shock waves from coronal mass ejections and other transient phenomena. For 3I Atlas, both tails are present, though their prominence depends on the comet's activity level and the observer's perspective. If the comet is viewed edge-on relative to its orbital plane, the dust tail may appear foreshortened, less impressive than when seen from an angle that allows its full length to be appreciated. The ion tail, being more radial and straight, is less dependent on viewing geometry, though it may be faint if the comet's gas production rate is low. Observations from multiple locations and times help reconstruct the three-dimensional structure, the true shape and extent of the tails in space. The composition of the ion tail can be probed through spectroscopy. Ionized carbon monoxide CO+ produces strong emission at specific wavelengths in the ultraviolet and visible. Water ions H2O+ and OH+ emit in the ultraviolet. Ionized nitrogen molecules, ionized carbon dioxide, even molecular ions like H3O+, the hydronium ion, all contribute features to the spectrum. Each species tells something about the coma chemistry and the ionization processes at work. The relative abundances of ions compared to neutral molecules reveal the ionization rate, which depends on solar UV flux, which varies with solar activity and with the comet's distance from the Sun. Dust composition can be inferred from scattered light. The spectrum of sunlight scattered by the dust shows subtle features, absorption bands or emission peaks corresponding to mineral composition. Silicates, for example, produce a broad emission feature around 10 microns wavelength, observable in the infrared. The shape of this feature depends on whether the silicates are crystalline or amorphous, on the specific minerals present: olivine, pyroxene, others. Organic compounds may contribute as well, though their spectral signatures are often more subtle, blended into the continuum. Careful modelling, comparing observed spectra to laboratory measurements of candidate materials, allows researchers to estimate the dust's mineralogy and chemistry. The dust tail is not static. Particles are continuously released from the nucleus as gas production lifts new material into the coma. These particles drift outward under radiation pressure, older particles having travelled farther, newer particles still close to the nucleus. The result is a tail that evolves over time, its structure reflecting the history of dust production over days and weeks. If the comet's activity increases, the tail brightens and extends. If activity decreases, the tail fades, though the particles already released continue their outward journey, gradually dispersing into space. Only took a few centuries, from Tycho Brahe's observations noting that comet tails point away from the Sun, to Biermann's recognition in the 1950s that this required a solar wind of charged particles to confirm the physical mechanisms at play. The recognition that two distinct tails exist, governed by different forces, came later still, requiring spectroscopy to distinguish ionized gas from reflected sunlight off dust, requiring careful photography to capture the different morphologies. Now, the distinction is well established, textbook material, but the details still surprise. Individual comets show unique behaviors, unexpected abundances, anomalies that challenge simplified models. The tails of 3I Atlas point outward, away from our Sun, but also, in a sense, away from the star system where the comet formed. The molecules and dust were assembled elsewhere, processed in another disk, another set of conditions, and now they are being stripped away, ionized, dispersed, redistributed into the solar system space. Some fraction of this material will eventually fall toward the Sun, spiral inward over millennia, perhaps be absorbed into the solar wind or swept up by a planet. Some will escape, pushed outward by radiation pressure and solar wind, eventually rejoining the interstellar medium, completing a cycle of matter exchange between stars. The comet is both visitor and contributor, arriving with cargo from afar, leaving some of it behind as it departs. The debris trail is subtle, nearly imperceptible, a diffuse scattering of particles along the comet's orbital path, Unlike the visible tail, which extends outward from the nucleus in a direction determined by radiation pressure and solar wind, the debris trail follows the orbit itself, marking the trajectory with microscopic grains too small to see individually, but collectively detectable through their scattered light. These particles are the smallest ejecta submicron dust, fragments of larger grains broken by collisions or thermal stress. Organic molecules polymerized into solid particles. They drift slowly away from the nucleus, dispersing along the orbital path, creating a tenuous ribbon of material that will persist long after the comet itself has departed. The trail is not dense enough to produce a meteor shower. When Earth passes through the debris trail of a periodic comet Halley, for example, or swift Tuttle dust particles enter the atmosphere at high velocity, heating by friction, creating the bright streaks we call meteors. But those comets have passed through the inner solar system thousands of times, depositing material with each passage, building up trails dense enough and wide enough that Earth's orbit intersects them annually. 3i Atlas passes once. The material it releases disperses into space along a hyperbolic path that does not intersect Earth's orbit, or any planet's orbit, closely enough for future meteor activity. The debris trail is an orphan, unbound, destined to drift through the solar system without ever encountering a planet, eventually spreading so thin that it becomes indistinguishable from the background zodiacal dust. The particles themselves are diverse. Silicate grains, crystalline or amorphous, composed of magnesium, iron, silicon, oxygen in various combinations, organic compounds, CH-on particles, as they are sometimes called, rich in carbon, hydrogen, oxygen, nitrogen complex tars and kerogens assembled from simpler molecules through radiation chemistry. Perhaps fragments of water ice, though ice sublimates readily at the comet's current temperature and distance. Perhaps metallic inclusions, iron-nickel grains, relics of stellar nucleosynthesis embedded in the comet during its formation. The exact composition varies from particle to particle, each one a microcosm of the comet's bulk composition, modified by surface processes and ejection dynamics. Radiation pressure acts differently on particles of different sizes. Micron-sized grains experience maximum effect, their cross-sectional area large relative to their mass, making them susceptible to photon momentum transfer. These are pushed outward most strongly, leaving the comet's orbital path quickly, dispersing into the broader solar system. Larger grains, tens of microns or more, are less affected, their greater mass requiring more momentum transfer to alter their trajectory significantly. They remain closer to the original orbit, drifting slowly outward but not escaping entirely. The result is a size-sorted distribution of small particles far from the orbit, large particles close to it, a gradient that reflects the balance between gravity, radiation pressure, and initial ejection velocity. The trail extends both ahead of and behind the comet along its orbit, though ahead and behind are relative terms in a hyperbolic trajectory. Particles ejected when the comet was approaching perihelion drift differently than those ejected on the outbound leg, their initial velocities combining with radiation pressure in different ways. The trail is not symmetric. Modelling its structure requires accounting for the time history of dust production, the size distribution of ejected particles, the radiation pressure efficiency as a function of size and composition, the gravitational perturbations from planets. The models are complex, the parameters uncertain, but the general structure can be predicted: a diffuse stream of particles, widening with time, gradually dispersing into the solar system's dust population. Detection of the debris trail is challenging. The particles scatter sunlight, but individually they are far too faint to see. Only in aggregate, when millions or billions of particles occupy the same region of space, does the scattered light become detectable. Ground-based telescopes, even large ones, struggle to resolve such faint, extended structures against the background sky. Space-based infrared observatories have better luck. Dust emits thermal radiation in the infrared, and the cold of space provides a dark background against which even faint emission can be detected. The trail appears as a faint line or arc, sometimes detectable only through careful subtraction of background sources and statistical analysis of the remaining signal. For 3i Atlas, the debris trail may never be detected. The comet's passage is brief, its dust production rate modest, the trail's geometry unfavourable for Earth-based observation. The opportunity to detect it exists for perhaps a few years after the comet's departure, while the trail is still relatively compact and has not yet dispersed into the general dust population. After that, the trail becomes too faint, too diffuse, effectively invisible. The material is still there, drifting through space, but undetectable, a ghost of the comet's passage, known to exist from theory but not confirmed by observation. Only took a few decades of infrared astronomy and spacecraft missions like IRIS and Spitzer to reveal that the solar system is filled with dust, that zodiacal light, the faint glow visible along the ecliptic at dawn, and dusk is sunlight scattered by interplanetary particles, most of them cometary in origin. The total mass is small, perhaps equivalent to a modest asteroid, but the distribution is vast, spread across the entire inner solar system. Comets continually replenish this dust as they sublimate, while radiation pressure and pointing Robertson drag slowly remove particles, either pushing them out of the solar system or spiraling them into the sun. A steady state is maintained, input balancing output, the dust population neither growing nor shrinking significantly over millions of years. 3i Atlas contributes a negligible amount to this population. Its single passage releases perhaps thousands or tens of thousands of tons of dust, trivial compared to the contributions from periodic comets that return every few years or decades. But the contribution is unique in origin. Particles from another star system mixed into the solar system's dust cloud. A contamination in the sense of introducing material with different isotopic and chemical signatures. Somewhere in the zodiacal dust, a few grains from 3i Atlas drift, indistinguishable by any practical means from the native population, yet foreign in their chemistry, carriers of information about another planetary system encoded in isotope ratios and mineralogy. The trail stretches across space, invisible, unmarked, a monument to the comet's passage that no one will visit, no one will study directly. It exists because physics demands dust is ejected, radiation acts upon it, particles disperse. The comet does not intend to leave a trail, does not mark its path deliberately. The trail is consequence, not purpose, a side effect of sublimation and solar radiation, written in scattered grains too small to see and too sparse to matter, except as data points in models, as theoretical constructs, as evidence of processes understood but not observed. The outbound journey begins not with a sudden shift, but with a gradual reversal of trends. The comet rounds perihelion, the closest point behind it now, the sun's gravity pulling backward rather than forward, decelerating the outward motion in the same way it accelerated the inward fall. The velocity remains high, hyperbolic, unbound, but the rate of increase slows, then stops, then begins a slow decline. The comet will never stop entirely, never turn around, but it will move more slowly at 5 astronomical units outbound than it did at 5 astronomical units inbound. Gravitational potential energy is being converted back from kinetic energy, the reverse of the infall process, symmetrical in physics, if not in observational consequences. Solar flux decreases. Each day, the comet is slightly farther from the sun, the intensity of sunlight slightly diminished. The decline follows an inverse square law doubling the distance quarters the flux. At 2 astronomical units, the flux is 1/4 what it is at 1. At 4 astronomical units, 1/16, the surface temperature responds, though with a lag due to thermal inertia. The nucleus taking time to cool as absorbed energy dissipates through radiation and sublimation. Water production, which peaked near perihelion, begins to decline. At 3 astronomical units outbound, Water vapour is still the dominant volatile, but carbon dioxide and carbon monoxide are gaining relative importance as water ice becomes less willing to sublimate at the lower temperatures. The coma begins to contract. Gas production decreases, and with it the outflow velocity and the extent of the expanding cloud. Dust production declines as well. Fewer particles lifted by the weakening gas flow. The comet dims, its brightness dropping as both the coma shrinks and the solar illumination decreases. For observers on Earth, the opportunity narrows. The comet, which was perhaps magnitude 10 or 11 at perihelion, too faint for the naked eye, but accessible to small telescopes, fades to 12, 13, 14, slipping below the detection threshold of all but the largest instruments. Observation windows shorten, the comet visible only in darker skies, requiring longer exposures, more sensitive detectors. Activity does not cease immediately. Even at 5 astronomical units outbound, carbon monoxide continues to sublimate, maintaining a faint coma, though much reduced from peak levels. The nuclear surface cools to perhaps 100 Kelvin, then 90, then 80, temperatures at which carbon monoxide production is slow but not zero. The comet may remain weakly active for years, producing a tenuous gas halo detectable only by the most sensitive instruments or by spacecraft in the outer solar system, if any happen to be positioned appropriately. But such detections are unlikely. The comet's trajectory does not bring it near any spacecraft, and ground-based observation at such distances is difficult. The thermal history of the nucleus is asymmetric. During the inbound leg, heat accumulated, penetrating deeper into the ice as the comet approached the Sun. By perihelion, the outer metre or so of the nucleus may have warmed significantly, creating a temperature gradient that extends into the interior. On the outbound leg, this stored heat continues to drive sublimation for a time. Even as the surface itself cools, gas diffuses outward through the porous matrix, escaping from depths where the temperature remains above sublimation thresholds. This delayed outgassing is subtle, a tail on the activity curve, measurable if observations are precise enough, but easily lost in noise. Rotation continues, unaffected by the changing solar flux. The nucleus spins at the same rate outbound as it did inbound, unless outgassing torques have altered the rotation state. Such changes, or possible jets of gas escaping from localized areas, can exert torque, slowly spinning up or spinning down the nucleus, or altering the orientation of the rotation axis. Over many orbits, these torques can significantly change a comet's rotation. For 3i Atlas, with only a single passage, the effect is likely small, but not necessarily negligible. Precise astrometry might reveal subtle deviations from the predicted orbit, non-gravitational forces caused by asymmetric outgassing, though detecting such effects requires long observational baselines and careful data reduction. The comet's trajectory carries it back toward the heliopause, though the journey will take years, perhaps decades. At its current velocity, covering an astronomical unit takes weeks. Covering 100 astronomical units takes years. The comet will cross the orbits of the outer planets Jupiter, Saturn, Uranus, Neptune, though not closely, its inclination and timing such that no close encounters occur. These crossings are geometrical facts, points where the comet's path intersects the planetary orbital planes, but without physical consequence. The planets are elsewhere in their orbits, unaware of the visitor passing through. Only took a few months, from discovery to perihelion to fading from view, for the entire observational campaign. The comet's passage through the inner solar system is brief, a window measured in seasons rather than years. Comets on long-period orbits from the Oort cloud may be observable for years as they approach and recede, their slower speeds and bound orbits allowing extended study. Interstellar comets, moving faster, offer less time. The observations must be opportunistic, concentrated into the brief period when the comet is bright enough and well positioned. After that, the opportunity is gone. Data analysis will continue for years. The spectra collected, The images taken, the photometric measurements recorded all require processing, calibration, interpretation. Light curves must be analysed for periodicity. Spectra must be compared to models and laboratory data. Orbital elements must be refined with each new astrometric position. Papers will be written, results published, debates conducted over interpretations and uncertainties. The comet itself will be long gone, fading into the outer dark, but the data remains, a record of its passage, a set of constraints on models of interstellar chemistry and planetary formation. Some questions will remain unanswered. The nucleus size will be uncertain, estimated within a factor of 2 or 3 but not precisely measured. The rotation period may be ambiguous, multiple solutions fitting the data equally well. Isotope ratios will have large error bars, some species undetected, others detected but with abundances too uncertain to draw firm conclusions. The dust composition will be inferred from scattered light and thermal emission, but the exact mineralogy will remain speculative. These limitations are accepted, understood as consequences of remote observation, of the vast distances involved, of the finite resources available for study. The comet does not know it is leaving. It follows the trajectory gravity dictates, cooling as it recedes, its activity declining to near zero, its coma shrinking to nothing. Eventually, it will appear again as it did before discovery, a dark, inert nucleus, too small and distant to detect, carrying its ancient ice back into the interstellar medium. The warming was an interlude, a brief exposure to stellar heat, an anomaly in the comet's long existence. Now, the cold returns, and with it, the silence. The questions accumulate, unresolved, layered like sediment. Where did 3I Atlas form, around which star, in which molecular cloud, under what conditions of temperature and pressure and elemental abundance? The spectroscopic data constrains possibilities, but does not determine answers. The isotope ratios, if measured with sufficient precision, might favour certain stellar environments over others, but the error bars are wide, the overlap between different models significant. A deuterium to hydrogen ratio slightly elevated compared to solar system comets could indicate formation in a colder region, or around a less massive star, or in a molecular cloud with different enrichment history. Or it could be within measurement uncertainty of solar system values, the difference illusory, an artifact of noise. The comet's age is unknown. It could have formed 4 billion years ago, early in the galaxy's history when star formation rates were higher and metallicity lower. It could have formed more recently, 1 billion years ago, or 500 million, ejected from a young system still clearing its planetary disk. Dating requires radioisotopes, elements that decay at known rates, providing chronometers that can be read if samples are analysed in laboratories. Uranium, thorium, potassium-40, aluminum-26 all have been used to date meteorites and lunar samples, but 3I Atlas is not a sample. It is a distant object, observed only through light, and light does not carry radioisotope abundances in any directly readable form. The age remains a matter of inference, of statistical arguments about how long an object might wander between stars before encountering another stellar system. How long has it been wandering? The trajectory can be traced backward, accounting for the sun's motion through the galaxy, the motion of nearby stars, the gravitational perturbations from massive objects encountered along the way. But each assumption introduces uncertainty. The galaxy's gravitational potential is not perfectly known. Encounters with molecular clouds, invisible at the distances and times involved, could have altered the comet's path without leaving evidence. The backward integration becomes increasingly uncertain, the cone of possible trajectories widening, until at some point, perhaps 1 million years back, perhaps 10 million, the origin is effectively untraceable. The comet could have come from almost anywhere in the solar neighbourhood, or beyond. Did it pass near other stars during its journey statistically? Likely. The galaxy is not empty. Stars number in the hundreds of billions. And though space is vast, Close encounters within a light year or two occur on timescales of millions of years for any given wandering object. But close encounter in galactic terms does not mean the comet would have been perturbed significantly, or captured, or even noticeably affected. A passage within 1 light year of a sun-like star would exert only a tiny gravitational influence. Not enough to bend the trajectory more than a few degrees, not enough to slow or speed the comet substantially. The comet would pass through, largely unchanged, continuing its journey through the interstellar medium. What will happen to it now? The outbound trajectory is predictable in the short-term geometry and gravity dictate where the comet will be in 10 years, 100 years, 1,000. It will cross the heliopause again, exiting the sun's domain, returning to the interstellar medium. Its velocity, relative to the local standard of rest, will be altered by the gravitational encounter with the sun deflected slightly, slowed, or sped depending on the geometry of the flyby. This change, though small, is permanent. The comet's future path through the galaxy is now different from what it would have been had it not encountered our solar system. Where it will go is unpredictable in the long term. Galactic dynamics are chaotic over timescales of millions of years. Small differences in initial conditions compound, trajectories diverging exponentially. The comet might pass near another star in 1 million years, or 10 million, or never. It might enter a molecular cloud, where drag from gas and dust could slow it, altering its trajectory, perhaps even allowing capture by a forming stellar system. It might be struck by a high-velocity particle, a micrometeorite travelling at a significant fraction of the speed of light, fragmenting the nucleus, scattering debris, or it might simply drift, undisturbed, for billions of years, crossing the galaxy in slow arcs determined by the gravitational potential of the disk and halo. Will it ever be captured? The probability is low, but non-zero. Capture requires a precise balance. The comet must approach a star at just the right velocity and angle, such that gravitational interaction reduces its kinetic energy below escape velocity without ejecting it back into interstellar space. This is more likely in dense stellar environments like star clusters, or in systems with massive planets capable of gravitational assists. In the sparse galactic disk, capture is rare. Most interstellar objects that encounter a star system pass through and leave. As 3i Atlas is doing now, could it carry life or the ingredients for life? The question is speculative, unanswerable with current data. Comets contain organic molecules. Amino acids have been tentatively identified in some cometary samples returned by spacecraft. Though the detections are contested, complex hydrocarbons, polycyclic aromatics, molecules with carbon-nitrogen bonds all are present. Whether any of these molecules are organized into structures that might be called protobiological is unknown. Whether 3i Atlas, in particular, carries such molecules is unknown. The spectroscopy reveals simple species water, carbon monoxide, cyanogen, but not the complex organics that would require higher resolution and longer integration times to detect. Panspermia, the hypothesis that life, or its precursors, might be transported between star systems via comets or other interstellar objects, remains on the edge of scientific respectability. The idea is old, proposed in various forms by Arrhenius, Hoyle, Wickramasinghe, and others. The challenges of significant radiation in space is harsh. Cosmic rays and ultraviolet light degrading complex molecules over time. The timescales are long, millions of years in transit, during which any biological material would need to survive without energy input, without repair mechanisms. Bacterial spores can survive in dormancy for thousands of years, perhaps longer, but millions. The question is unresolved. Experiments on the International Space Station have shown that some organisms can survive exposure to space for limited durations, but scaling that to interstellar timescales is speculative. Only took a few centuries of scientific inquiry to reach this level of uncertainty with confidence. Earlier, the questions would not even have been asked. Comets were omens, not objects of empirical study. not carriers of chemistry or potential biology. Now, the questions are well posed, the uncertainties quantified, the pathways to answers understood even if the resources or technology to follow those pathways are not yet available. 3i Atlas will leave without providing those answers. It was here. It was observed. It contributed data. But the deeper questions, where it came from, where it is going, what it carries within, remain open, awaiting future visitors, better instruments, or perhaps sample return missions that can intercept interstellar objects and bring fragments back to Earth for detailed analysis. The comet continues outward, indifferent to the questions. It is ice and rock and organic molecules, governed by physics, without awareness, without purpose. The mysteries are human constructs, products of curiosity and the desire to understand. The comet simply is. The comet fades from instruments, first from the smallest telescopes, then from mid-sized observatories, finally from the largest apertures on Earth and in space. At magnitude 18, it is detectable only with long exposures and careful tracking, the signal barely distinguishable from noise. At magnitude 19, only a handful of facilities worldwide can still register its presence, and only under optimal conditions: dark skies, no moon, stable atmosphere. At magnitude 20, it slips below the practical detection threshold for all but the most determined observers, those willing to stack dozens or hundreds of images, pushing the limits of what photons and sensors can reveal, and then, even those efforts yield nothing. The comet is still there, still moving outward, still reflecting sunlight, but the reflected light is too faint, the photon count too low, the background sky too bright by comparison. The final observations are logged, the last data points added to the archive. A spectrum taken 3 months after perihelion shows fading emission lines, gas production declining but not yet ceased. A photometric measurement 4 months out confirms the predicted brightness curve, the comet dimming as expected. An astrometric position 5 months out refines the orbital elements slightly, reducing uncertainties, confirming the hyperbolic nature of the trajectory, and then silence. No more data arrives. The observing campaigns close. Telescope time is reallocated to other targets, other comets, asteroids, distant galaxies, the myriad objects competing for attention. The comet crosses 6 astronomical units outbound, then 7, then 8. At this distance, even if it were still producing gas, the coma would be too faint to detect from Earth. The nuclear surface has cooled to perhaps 60 or 70 Kelvin, too cold for water, too cold for carbon dioxide, marginal even for carbon monoxide. Any remaining activity is a trickle, molecules escaping at rates too low to create a visible coma. The comet returns to dormancy, the state it occupied for most of its existence, the state it will occupy for the remainder. Sunlight still reaches it, diminished but present. At 10 astronomical units, the sun appears as a bright star, smaller than it does from Earth, but still the dominant source of illumination. At 20 astronomical units, it is merely one bright point among others, no longer obviously special to an observer stationed on the comet. At 50 astronomical units, the sun's light is faint, the solar disk too small to resolve with the naked eye, the warmth negligible. The comet's surface temperature asymptotically approaches the background temperature of space, the cosmic microwave background at 2.7 Kelvin, supplemented slightly by starlight from the galaxy, perhaps settling around 10 or 15 Kelvin, cold enough that all volatiles freeze, that molecular motion slows to quantum vibrations, that the nucleus becomes inert once more. Years pass in this outbound drift. The comet is forgotten in the sense that active observation ceases, but not in the sense that the data disappears. The measurements remain in archives, accessible to researchers, cited in papers, incorporated into models. The comet becomes a case study, a data point in the small but growing catalogue of interstellar objects. comparisons are made to other visitors. Oumuamua, the first confirmed interstellar object, detected in 2017, remarkable for its elongated shape and unusual acceleration. 2I Borisov, the second, a more typical comet, observed in 2019 showing gas production and a coma, chemically similar to solar system comets. 3I Atlas adds to this sample, each object revealing something about the population of wanderers between stars, the diversity of planetary system debris ejected into the galaxy. Statistical arguments are made. If 3 interstellar objects have been detected in a few years of survey operations, how many must be passing through the solar system undetected? The detection probability is low objects must be bright enough, pass close enough, move through surveyed regions of sky. Models suggest that for every detected object, thousands or tens of thousands pass through unobserved. The galaxy, it appears, is awash in such debris. A vast population of comets, asteroids, and perhaps larger bodies, drifting between stars, a byproduct of planetary system formation and evolution. Most are small, dark, inactive, effectively invisible unless they happen to pass very close to the sun and warm enough to outgas. The comet itself is unaware of its classification, its contribution to statistical models, its role in scientific discourse. It continues along the trajectory gravity dictates, moving at a velocity measured in kilometers per second but experienced as stillness. The stars so distant that they appear fixed even over years of travel. The sun recedes, one star among billions. The solar system, a region of space briefly visited and now behind. The galaxy rotates, stars orbit the galactic center, spiral arms turn, and the comet moves through it all, a mote tracing a path determined by ancient forces. Decades into the future, the comet will cross 100 astronomical units from the sun, then 200 distances where even the most sensitive instruments could not detect it if they tried. The heliopause, that boundary between solar and interstellar plasma, is crossed again, though the exact moment is unmarked, unwitnessed. The solar wind fades to irrelevance. The magnetic field embedded in that wind no longer reaches the comet. Cosmic rays, high-energy particles from supernovae and other sources, are no longer partially deflected by the heliosphere. The radiation environment shifts subtly, returning to the conditions the comet experienced during its interstellar journey. Only took a few years to cross through the heliosphere, from entry to exit, a brief interval in the comet's history, a moment of warmth and activity surrounded by eons of cold and silence. And now the cold returns, as it must, as physics demands. A surface, darkened by cosmic ray processing during the long approach and briefly refreshed by sublimation near the sun, begins its slow weathering once more. Radiation breaks molecular bonds, polymerizes simple organics into complex tars, sputters atoms from the surface layer by layer. Over millions of years, the outer few centimeters will be processed, altered, transformed into something that barely resembles the original material. But beneath, the interior remains pristine, unchanged, a frozen archive of the comet's formation conditions. The stars ahead are distant, their light reaching the comet after journeys of years or decades. The comet does not travel toward any particular star, but simply outward, into the general direction determined by its encounter with the sun. Centuries from now, millennia, the comet will be light years from our solar system, still moving, still carrying its cargo of ice and dust and organic molecules, still a fragment of another star's history adrift in the galaxy. Whether it will encounter another star, whether it will be warmed again, whether it will be observed by intelligences yet unborn, these are questions without answers. Outcomes determined by probability and time, by the chaotic dynamics of stellar motion, and the vast emptiness between suns. The journey continues, as it has for uncountable years, as it will for uncountable years to come. The comet is patient, in the way that inanimate objects are patient, simply existing, following the path that gravity and momentum prescribe. And the galaxy, patient in its own vast way, continues its slow rotation, its stars forming and dying, its spiral arms compressing gas into new stellar nurseries, its wanderers drifting through the dark, connecting star to star through the silent exchange of matter, writing a history in ice and rock, and the faint traces of light scattered into space. The darkness is not absolute. Starlight persists, faint and cold. Photons from distant suns falling upon the comet's surface at rates too low to warm, too sparse to measure, yet present nonetheless. The galaxy glows softly in infrared, the combined thermal emission of billions of stars creating a background barely distinguishable from the cosmic microwave background itself. The comet drifts through this dim illumination, a speck among specks, indistinguishable from the countless other fragments wandering between stars, all of them silent, all of them patient, all of them following trajectories written in gravity and time. The surface temperature settles toward equilibrium with the galactic radiation field. 10 Kelvin, perhaps 12. Cold enough that helium would be liquid, though there is no helium here. Cold enough that molecular motion is quantum vibration only. Atoms locked in lattice positions, held by forces that operate at scales where classical mechanics yields to probability and wave functions. The ice does not flow, does not creep, does not change except through the slow accumulation of cosmic ray damage. One particle at a time, one broken bond per century per cubic centimetre, a rate so gradual that geological time is required to notice. The comet does not measure time. It has no clock, no internal process that marks duration. Days and years are human constructs, tied to planetary rotation and orbital periods, meaningless in interstellar space where no sun rises, no seasons turn. The comet simply persists, moment following moment in succession without count. Existence stretched across intervals that dwarf human history, that exceed the lifespan of civilizations, that approach the age of stars themselves. Somewhere far behind, the sun continues burning, converting hydrogen to helium, radiating energy into the void. Planets orbit, moons circle planets, asteroids tumble through the inner system, comets fall from the Oort cloud. The solar system continues its processes, indifferent to the visitor that passed through and departed, unaware of the fragment of another star's history that briefly warmed in its light. The exchange is complete. 3i Atlas arrived carrying chemistry from elsewhere, left behind a trace amount of dust and gas, and departed again. The solar system slightly enriched by foreign matter, the comet slightly altered by solar heat. Both continue, changed infinitesimally. The interaction noted by those who observed it but forgotten by the universe itself, which does not remember, does not record, simply unfolds according to physical law. The comet moves outward still, though outward loses meaning as distance from the sun increases. Direction becomes arbitrary in the galactic frame. The sun merely one reference point among many, no longer special, no longer the source of heat or light or gravitational dominance. The comet orbits the galaxy now, as all objects in the disk do, moving in a slow ellipse around the galactic centre, 200,000 trillion kilometres away, a journey requiring hundreds of millions of years to complete. The comet has made this orbit before, many times perhaps, and will make it again, if it survives, if it is not disrupted by collision or gravitational encounter, if time permits. The galaxy itself ages, stars form in nebulae, burn through their fuel, die as white dwarfs or neutron stars or black holes, returning processed material to the interstellar medium. The spiral arms rotate, density waves compressing gas, triggering star formation, then dispersing. The Milky Way will collide with Andromeda in a few billion years, the two galaxies merging, their stars and gas mixing, though individual stars will likely pass without collision. the distances between them too vast. The comet, if it still exists then, will be flung onto a new trajectory, the gravitational chaos of the merger altering orbits, sending some objects into the intergalactic void, others into the merged galaxy's core. Its fate is written but unreadable, determined by events that have not yet occurred, by interactions that cannot be predicted. For now, there is only the drift, the cold, the silence, the patient persistence of ice and rock and frozen molecules, moving through darkness at velocities measured against distant stars, crossing light years over timescales that erase memory and meaning. The comet does not know where it came from. It does not know where it is going. It does not know that it was observed, measured, catalogued, studied. It simply is, as it has always been, a fragment of cosmic debris, a carrier of ancient chemistry, a wanderer in the vast, slow turning of the galaxy. And in that wandering, in that cold persistence, there is a kind of rest. Not sleep, for the comet has never been awake. Not peace, for it has never known conflict. But a stillness, a continuity, an existence without change or effort. Just the slow, inevitable unfolding of trajectory and time, gravity's patient pull, the quiet passage through the dark, the stars wheel overhead, imperceptibly slow. The galaxy turns. The comet drifts, outward and onward, into distances we cannot follow, into futures we cannot know, carrying with it the unanswered questions, the unresolved mysteries, the chemistry of another place and time, preserved in ice, silent, timeless, alone.